to implement these beehive shape comparing to this very straightforward square, right? So, so far, let's do a quick summary. So far, we motivate the we introduce the motivations to image and video signal compression, communication, processing. Okay, and we cover two major parts of our framework, of our compression framework: the quantization part and the variable length part. Okay, let's take a break, and when we go back, we're going to start thinking about the T-box and how to design the transform that can be used together with the quantizer and the entropy coder to connect them together into a nice complete codec. Okay, so see you back here in about 10 minutes. Now, so let's see. We cover quantization, we cover entropy coding, so we cover 2 out of 3 in our original transform coding framework. Okay? So the last step to complete the entire framework is the transform part, or the prediction part. Okay? And we're going to try to do these things today. So we would be lucky if we cover up until this point. Okay? From now until 12. So we'll first start with simple prediction. Okay? Prediction is still, say, I'm at location K, okay? And I have my neighbor at location K minus 1, K plus 1, K minus 2, K plus 2. How do I predict myself from the observed neighborhood? Okay? That's the first thing that people try when they try to decorrelate something. So that's the prediction technique. Then after prediction, people get a little smarter. And people say, instead of predicting one guy at a time like that, okay, which can be pretty inefficient, okay, we're going to try to predict an entire vector together, or an entire block together. And that's where the transform comes in, right? We talk about, I'm going to talk about vector space and how to do linear predictions, okay, of a vector space using the fewest amount of coefficients, right? So it depends on the basis functions, right? So you design a good basis functions which will allow you to approximate whatever signals using a very few number of coefficients. And instead of sending the pixels or the samples or whatever over, we send the coefficients over. We send the coefficients over, right? At the other end, at the decoder, the decoder will use all the, it knows the basis function that the encoder use those linear combination, reconstruct. And that's where you have the state-of-the-art transformation techniques, okay? And so then, the next question to ask is, how do we design the basis function, okay? So that's the main part of today's lecture. I'm going to try to show you the optimal linear transform and hopefully convince you that under certain assumptions, we have the discrete cosine transform which come pretty close to the optimal linear transform, the KLT here. And then we also have techniques like the weighted transform, which is the new kid on the block, right? New guys that coming up the rank that can do also very, very well. So, and in our MATLAB demos and exercise, we're going to try to compare different transforms, right? And hopefully convince you that some will perform better than others. Okay? So obviously, wavelets perform slightly better than the discrete cosine transform when it comes to only images, still images. But when it comes to video, this guy is still holding the lead. Okay? And obviously, I have to defer that until tomorrow when we talk about video coding. So the reminder is we cover E, we cover Q. Okay, we kind of know the behavior of these guys pretty well. Okay, so the main job is to define T and the appropriate T inverse so that we will complete the framework. Okay? And typically, people will do either prediction here or transformation here. Okay? Some kind of decorrelation engine. Okay? Take away the correlation between the sample of the input signals. So, so far we have only dealt with memoryless model. That means we never cares about the neighbors. We try to do a little bit with run length coding, but other than that, we're processing one guy at a time, one sample at a time, one coefficient at a time. Okay. There is usually very strong correlation between neighboring symbols, and we can easily confirm in MATLAB, right? We can just randomly go into any natural image you want, pull out an 8x8 or 4x4 plot, and see the behavior of the coefficient, and you can see that most of the time they're very close to each other. Okay, meaning that there are a lot of correlation, and we can so like Edmund showed yesterday, the random image doesn't have any structures, right? Doesn't seem to have any interesting behavior, but the natural image seems to have a lot of correlations, a lot of edges going together, a lot of smooth regions, right? These are the things that we can take advantage of to do very good compressions, okay? So the simplest prediction scheme that we can do is to take the difference, okay? Right? You just take the difference between you and the neighbors, and just instead of encoding each samples, we encode the difference. Okay, that will reduce the entropy a little bit. Okay, but we can do a lot smarter things. Okay, so the most primitive prediction techniques is called DPCM, or differential pulse code modulation. Okay, just a fancy name for this operation. Okay, this operation is this: I take my input signal X, okay, and I subtract my neighboring samples, which is xn minus 1, I have the difference, okay? And instead of doing x and x minus 1, I just feed d into q, and then that's my encode. Okay, so instead of encoding x, I encode the difference between x and the neighbors, okay? Feed it into q, feed it through the entropy coder here, go through the communication check. Okay, how do we reconstruct?
We use dn and is and minus 1.
Yes, right? We add d back to x and minus 1, we construct x, okay? So the reconstruction looks like this. So this is the inverse quantizer. You have the d hat, okay? Now, and then you add it back with the x hat n minus 1, and you get back the x hat. Now, if you throw the quantizer away, if you make dn equal to d hat n equal to dn right here, you can easily show that you get perfect reconstruction. Okay, you get exactly yourself back. Okay. Now, so the quantizer determines the trade-off between bit rates and reconstruction quality right now, right? Now, so yeah, let's do this analysis. Okay. Again, d hat is d plus q. That's our quantizer model. Okay. And so d hat is there, okay? So I have d hat equal to d plus q, and then in the encoder I have d equal to xn minus 1. So at the decoder I have x hat equal to d hat plus x hat, okay? So let's start with 0, okay? D hat of 0 is just d0 plus q0. So I reconstruct x hat of 0 like this, okay? Now, x0 is the starting point. There's no neighbor, right? Or there's no previous observation. So you just do it by itself. Okay, there's no difference, right? You just quantize x hat x directly. So x hat is just x0 plus q0, which is the error you make, okay? But now the problem comes when we do the next step, okay? So the d hat in the next step, okay? And this is the reconstruction. So x hat 1 is equal to d hat 1 plus x hat of x0 based on these formulas. And substitute everything in. Okay? I have something like this. Okay? Now, what is the problem? The problem, I manipulate the, okay, so basically just using these equations, I manipulate it to get it into this form, and I'm going to see that xs1 is equal to x1 minus x0. Okay, it looks like our original prediction scheme, and then all this. Okay, so you will be able to show that x hat is equal to x hat 1 is equal to x1 plus q0 plus q1 plus q0 plus q1. Okay, that's a significant step.